Can start now, Camila. Te puedes empezar.
A todos al 20º Congreso Chileno de Ingeniería de Transporte. Hoy día tenemos al profesor Kay Axhausen que va a presentar. Les cuento que esta presentación va a ser en inglés y por lo tanto si ustedes necesitan tener el traductor simultáneo, tienen que apretar abajo donde aparece Interpretation, ven que aparece un mundito. Si apretan en ese link van a poder ver toda la presentación en español. Vamos a repetir esto en el chat, pero por favor para que lo aprieten al tiro porque ahora yo voy a empezar a hablar inglés también. Así que eso. Okay, welcome to the 20th Chilean Conference in Transport Engineering, which for the first time is being held online. We have today Professor Kay Axhausen, who is presenting about travel behavior during COVID and the simulation of epidemics, the case of Switzerland and EPISIM. Kay Axhausen is a professor of transport planning at the ETH in Zurich. Before he worked at the Leopold Frances Universität, Innsbruck, Imperial College London, and the University of Oxford. He has been involved in the measurement and modeling of travel behavior for the past 37 years, contributing especially to the literature on stated preferences, microsimulation of travel behavior, accessibility, valuation of travel time and its components, parking behavior, activity scheduling, and travel diary data collection. Current work focuses on the agent-based microsimulation toolkit MATSIM, and his current GPS tracking study is part of his work on modeling the COVID-19 pandemic, which he will be presenting now. So at the end of the presentation, we will have time for Q&A questions. If you have any questions during the presentation, please write them in the chat window. And at the end, if we have any questions, you can raise your hand and I'll try to give you the word, well, if there's enough time. If you need to write any questions in Spanish, please do in the chat window and I'll make my best to translate them as well as I can. So without further ado, please, Professor Kay.
Thank you very much, Camilla. It's a great pleasure to be here. And I'm happy to present the work. And I'm happy to hear that it's the 20th conference, so your conference is about as old as the similar one we are organizing in Switzerland to give a chance for everybody to meet in the subject area and to find out what is happening around in the country in that year. Okay, let me talk about COVID and its simulation. As everywhere, Switzerland has been affected by COVID, and one of the responses has been to start up a research project, a large-scale one, by the Swiss National Research Foundation under the title National Research Program 78. I'm involved, or my team is involved, in this one of those projects together with colleagues from ETH, a further university in Basel and various other schools around the country. We also have advice from colleagues from Berlin, Paris, and ETH. In addition, I will present work which is based on the work of Stefan Müller, Stefano Pinazzi, and Joe Malloy, and I want to acknowledge their contribution here at the start of the talk. Okay, let me start with some numbers about how COVID has played out on the travel behavior side in the country. Before we did that, before we were able to check that, to track people, we conducted a tracking study in the fall of 2019. It was called MOBIS, and is and was a virtual mobility pricing study which focused on car and transit users. And we focused on people living and working in the agglomerations of German and French-speaking Switzerland, so not the very rural parts of the country. And we had the advantage that we were tracing 3,750 people for 8 weeks. So this gave us a very good idea of travel behavior in Switzerland before COVID started. We paid 100 franc incentive, which is about $100 US for them to participate. And the participation rate was actually quite high. 25% of the eligible participated. And the sample is roughly representative on all the usual dimensions you think of: age, gender, income, education. The technology we used is called Catch-A-Day. It's an app provided by MotionTag, which is a well-known firm in this market of providing tracking software for transport studies. Now, just because it's interesting, let's talk briefly about MOBIS. The key point was virtual pricing works. So you can incentivize people to change behavior in this way, which is there, but relatively unspecific. So the observed elasticity, price elasticity of -0.3 is actually probably at the lower range of the values you would obtain if you did price externalities properly and very targeted. We had tried in the MOBIS study also to have an information-only group, but there we saw that it didn't work, or it didn't work enough. It worked for some subgroups which were very altruistic, but for the population as a whole, nudging didn't work. For those who are interested, the final report is available at the website at the URL I show here, and the slides will be made available on the E40 webpage later, and I'm pretty sure at the conference webpage as well. So MOBIS worked, but that's not really what I'm supposed to talk about. I want to talk about MOBIS COVID. So what happened was that about 200, 300 people were still tracking a couple of weeks after the study had ended. And when we saw that, we decided to re-invite everybody of those 3,750 people to help us understand the COVID impact. So we invited them to reinstall the app if they had already deleted it, and to join again. And you can see on this graph that a very substantial share of people did. Over 1,000 joined again, and they stayed with us. Obviously, we had some people leaving us because maybe they had an update of the operating system, they got a new smartphone, they were just tired of it. But even at the beginning of the second wave, we still had 400 people. We then re-invited everybody again, and we got another increase to about 600. And then from the fall of 2020, Link, which is a market research firm in the country, volunteered to provide us further participants. So we have a very large sample of ongoing observation of the travel behavior around the country. We are not unique in Switzerland. There's a second private commercial sample which is also observing what is happening as it happens. Okay, what are the key results which we observed? The main result is that the share of people leaving the house changed. Now, if you look at the graph, you will see in gray the case numbers for 20 and 21. And you can see that in 21, the cases of people in hospital were quite substantial, but you also see that the first wave was not really as threatening as the second wave of the fall and winter of last year. Now, how much did this impress the Swiss when they traveled? Look at the blue line, which gives you the share of people leaving the house on any one day before COVID. And you can see that this is about 95%, 96%, obviously lower on weekends, but this is kind of what you would expect, that people leave the house. You can see the drop over Christmas and a resumption in the spring of last year, winter of last year. And then you see COVID arriving when the red line starts to drop. And yes, during the lockdown, only about 50% of people left the house, but still 50% of people left the house, which tells you that the lockdown was never as stringent in Switzerland as it was, for example, in Madrid or in Spain or in France. And it recovered then relatively quickly as people got used to the condition, as people saw that leaving for a walk, leaving for jogging was perfectly all right. And obviously leaving for shopping and going for the hospital and doctor was perfectly fine. And by the summer, it started to stabilize, but it started to stabilize at a value of about 5 to 10% lower than before. And this lower value has been retained ever since. You can see that as the yellow line, which is 21, essentially overlaps the experience of 20. So people have learned to stay at home, either because they don't want to leave or because they don't have to leave anymore because they're working from home. And that obviously is a major impact which has potential to be long-lasting if people adapt their lifestyles around the ability to work from home. Sorry about this. Now, the second thing which obviously happened was that the number of trips and the activity spaces changed. The number of trips are the blue lines. And you can see that as the lockdown happened, just at the very beginning of the x-axis, you had a drop by about a factor of 1 trip a day was lower than before. And you can see as well that people recovered pretty quickly. And then you had the second wave, but it's also Christmas and winter, but second wave effect. And now it's actually back up at a value which is higher than the one before. Now, we have to be careful there. There might be an artifact in the way motion tag is processing the data, but still we are back to normal in terms of numbers of trips. In terms of the space, the duration and length of the trips, we had a massive collapse when lockdown happened. The activity spaces changed by 80%. People just didn't leave the home. And if they did, they didn't leave far. So yes, they left the home, they made trips, but they stayed close to where they lived. And that, in line with the recovery of the number of trips, a bit slower, they recovered the activity spaces. So they went as far as before. We had then the second wave and the winter effect, and then finally, we are back to normal. So the Swiss are traveling as far as before. They're traveling as often as before when they leave the house. Please remember, fewer people are leaving the house. Now, if you look at the modes, I'll show you the changes in person kilometers traveled by mode on the next graph, on this graph. You can see the period before the lockdown, the usual variation, the usual impact of the weather, the usual impact of Christmas, New Year. But then you see the collapse of travel after lockdown. Actually, it started a bit before as people were seeing the pictures and the reports from Lombardy, which was the first hotspot in Europe. Public transport, which are the dark purple blue lines, recovered, but never to its full extent. So in Switzerland, public transport is still about 20% down on previous numbers. And this is obviously a major worry for the operators and for public policymakers. Because car travel, the yellow line, has recovered fully, and walking and bike as well. Now, the one thing which raised a lot of hopes when it became obvious was what was labeled the bike boom. So in the spring of last year, you had many people buying bikes, e-bikes or normal bikes. There were reports of the dealers being out of stock as people acquired bicycles. And yes, we see that big increase in passenger kilometers, but you have to remember it's from a low base. And what you also see in the spikiness of the increases of walking and cycling, that it's very weather dependent. So if the weather is good, we see massive increases. And we haven't done the full analysis, but if you compare 1920 and 1921, it seems as if in the first summer, it was a further increase. And it's going to be interesting to see if that increased use of bicycling actually becomes permanent. People get used to it and actually integrate it into their scheduling. Okay, so what did we see? We saw the decrease in the share of people leaving the home. We saw the recovery in terms of trip making and distance travels, and we see the drop in public transport over the period. Now, one way of explaining this collapse in rail freight travel in particular is to look at the value of travel time savings and to see if they have changed over the period. I apologize for the axis description being in German, but let me briefly translate this. So what I show you on the y-axis is the value of travel times estimated with appropriate discrete choice models, and at the x-axis, the different periods. And it's the reference periods before, and then phase 1, phase 2, and then after the lockdown. So it covers most of 20. And you can see that during phase 1, which is the lockdown phase, the value of travel time savings increased massively. But they fell again as people relaxed, as the restrictions relaxed, and as the Swiss felt that they had this thing under control, at least at an individual level, if not at a collective level, because Switzerland still has substantial case numbers. But the excitement about them is not nearly as strong as it was in the first weeks, when we didn't really understand what the illness was about. Now, one of the big issues we have is to give advice to policymakers on the pandemic and its course and the way it spreads. And then to assess what the different measures actually achieve if they're implemented. In the first couple of weeks and days, there was a large clamor for such models. Although increasingly one gets the feeling that the policymakers are not really listening to the models at this stage. It becomes much more driven by the policy conflicts inherent in implementing strong restrictive measures. Now, as it turns out, MatSim, which is the standard agent-based tool which my group and Kay Axhausen's group in Berlin are working on, are able to help. Sorry. The standard models which the epidemiologists are using are the first three types. And they generally assume that the population as a whole is just one big soup and everybody is in contact with everybody else. And these SEIR models, suspectable, exposed, infectious, removed, are standard mathematical models using differential equations to make the predictions of the numbers. The epidemiologists very early learned that this was a bit too crude, so they started to compartmentalize it. They started to introduce social networks or network contacts in their models, but still aspatial. And then there are some models proposed by transport people which focus on aggregate networks of co-presence in vehicles, but not outside. And what we suggest, based on earlier work, which was done to model an influenza epidemic in 2004, is to look at the networks of co-presence in MatSim, in an agent-based transport simulation, and to repeat those days again and again, and keep track of the agents and their health status. So it's these model of repeated networks which are at the basis of the MatSim EpiSim approach. This work was essentially the PhD of Timo Schmidczek in collaboration with Michi Balmer, who was one of the core developers of MatSim, and the other people listed here. And he used it to look at the 2003-2004 influenza epidemic. This paper came back to the mind of Kai Nagel, and he revived the code and applied it to his model of Berlin, his MatSim model of Berlin. And we in Zurich are building on that work to now model Switzerland and actually do a bit more in the course of that project. So what is co-presence? We have to realize you have to be in the presence of an infected person to get infected. So you want to know who is meeting whom in a particular space at a particular time for a particular duration, and what other persons are present. But this is exactly what a transport model does. At least the fancier ABMs and agent-based models. It tells you where the population is at any one point in time, when they start to be together, how long they are together, and who is there, both during the activities as well as in vehicles if they travel jointly in a bus, a metro, or a car. Sorry about this. So this is the idea. If you look at these bars, these are joint activities, and activities means that multiple people are there. And we can follow the red circle, which is the agent which are interesting, as it moves from activity to activity and therefore meets other people. The longer they are jointly present, the larger are the chances that they infect each other. But we also see that the people who have been with the red agent leave and might infect others. So we can construct the network of infections, do the tracing, which none of the societies around the world has been able to implement or able to implement at scale. We can do this in the model, and we can keep track of how long they are infectious and whom they meet during that time. Now, MatSim is an agent-based model. It is based on an agent population, which describes all the actors in a particular study area, Switzerland, for example, or Berlin. And there's a couple of others who have now started to use this approach. It generates the network of co-presence for one day, because MatSim is a transport model, so we're interested in an average work day, just like most other people. So we only have one equilibrium state. And we have an infrastructure to replan these days if people change behavior. And this is the basis of our following work. As it happened, Kai had a model for Berlin. We had a model for Switzerland. And I tell you a bit more about it. Before I do that, let me just remind you of what MatSim does. MatSim is an iterative model which starts with a scenario. The scenario includes the network, the timetables, and the population and its activity plans for the day. It then simulates those activity plans to obtain the generalized cost of travel and the travel times for each of the agents. It then judges those plans, scores them, and looks at which days were good days, and then takes a random sample of the agent population and allows them to replan, to find new days, changing modes, changing destinations, changing departure times, changing durations, till they are in equilibrium where they don't want to change their day again. This is computationally very involved, and that's why we generally only do an average day. And happily, we had done this. So we were starting with the results file of this Switzerland simulation. MatSim is by now a very large open source software package developed over the last 15, 16 years by a score of PhD students since then. We have pipelines for scenario generation so that we can reproduce our results, OSM readers, GTFS readers, and GTFS mapping facilities. We can generate populations from scratch. We have tools to implement and impute traffic signals. We have, because computation time is crucial, we have versions which are faster than the standard MatSim you can download at matsim.org. Both Equasim to include random utility mode choice models, Hermes for a faster traffic flow simulation, Penazzi's data law to form super networks and not model every agent every time. There is a tool to calibrate the parameters by Gunnar Flötoet and others. And then there's a couple of external products which allow you to look at the results and edit the scenarios and run the management. So it's by now starting to become handleable for starting groups who don't want to invest all that effort. There are tools which allow you to get into it in a reasonable time. Now, what we want to do is obviously to assess the impacts of measures. For example, what happens if infected people have to quarantine for 5 days, 10 days, however long the governments decide? You want to know what is the effect of home office, what is the effect of homeschooling? What is the effect if the group sizes are limited, which was one of the policies which was adopted, for example, for restaurants, that only 2 people or 4 people were allowed to sit around the table. And then there's obviously restrictions on the distance you were allowed to travel. For example, if I remember right, in Israel, you were not allowed to go further than 1 kilometer away from your home, which again limits the chances that you meet others, and therefore you reduce the mixing of the population, which is what you want to do. Now, so what does EpiSim do? EpiSim is an add-on to MatSim. It takes the MatSim results of the equilibrium day and repeats it and repeats it and repeats it. It doesn't change the results. It only looks at the infections. It does change some things, but I'll come to that in a sec. It then, as I said, traces one person, one agent through these multiple days. Let's say 120 times this equilibrium day is repeated. It calculates how many people the person meets and for how long, and calculates how likely it is that the person gets infected by an infected person presence in that room during that activity. And then there's a couple of simple measures which are able to model kind of the most important measures. For example, you remove affected agents from activities. You can implement quarantines. You can implement restrictions on travel. You can model the effect of mask wearing. And later on, you can model the effect of vaccination and how long it takes before you have a full impact of the vaccination. It's not very subtle because the behavioral changes which we are seeing, that people are traveling less far, that they are moving less out of the house, that isn't included as models. And this is something we are working on and want to improve. The key of EpiSim is that it collapses all of the infection process into a probabilistic model. It calculates the probability of infection by this exponential function, which accounts for how many people are in that joint activity, how many viruses are shed or taken in, how long you are jointly with other people, how suspectal you are, and whether you're outdoor or not. And for each of those parameters, we have made assumptions or have taken values from the literature. The theta in the formula needs to be calibrated because at this point, nobody really knows what we should take there. So we calibrate this against observed trends. And this is tricky because the dynamics of change as the virus population changed. We all know about Delta and its higher infectiousness. So we have to account for that in different periods of the pandemic. The other things we know from the model, so we are well placed. Now, when a person is infected, then it takes a certain time before it becomes infectious. And as you can see here, we are taking from the literature values about how long it takes before a person becomes infectious and the variance of that as well. And then the person becomes infectious, then the person or the agent might heal asymptomatically, it might get symptomatic, it might recover, it might get seriously sick, it might recover, it might become critical, and then it might become seriously sick again before the person, the agent, recovers. And we are taking the observed median and standard deviations from the literature, from the medical literature, to formulate our models of calculating the probabilities of each of those transitions. Now, for Switzerland, what did we do? We had a model already for previous projects, so it was well used and trusted. It is based on an OSM network. We have all of the public transport timetables in the country, the main service from the SBB, as well as all the regional providers and regional railways and public transport undertakings. We have access to the actual population of the country because we have access to the federal population registry. Then the travel behavior we have taken from the microcensus 2015, which is the National Travel Diary. We could have replaced it by the MOBIS data, but we didn't do that because MOBIS was only 3,700 people and the microcensus is 60,000. So we stayed with that. And the MATSIM implementation was validated against traffic counts and mode by distance distribution and modal shares. So it's a well-calibrated model. So we started with that. And then we made certain assumptions based on the observed behavior of the Swiss. One of the main things is obviously mask wearing. Mask wearing in Switzerland started a bit slow. It took till October before mask wearing became obligatory in public transport. And then it took a while for people to adopt it themselves. These are the curves which are based on measurements and observations in the country. And this is what we implemented in EpiSim to reflect that. We then looked at the role of the imported cases because of the epidemic came in from abroad. But it's very tricky to identify the first carriers of the disease. In particular, as we all know, COVID is asymptomatic for a huge chunk of the infected. So they don't even know that they were ill. So we calibrated by backwards calibration the number of imported cases and then started from those onwards. And we did this both for the first wave and then later for the second wave, because that was the only way we could make it work. And that's a big issue in all of these simulations, that you have to make assumptions or calibrate it because you just don't know how many people are brought the disease into the country. Now, when you do that, you can compare against observed numbers. Now, COVID has been a bummer because the public interest in good numbers was quite limited when we think about it. Yes, the numbers for the cases in intensive care and being hospitalized were well covered. And you can see that the blue line, which is the real numbers, are well calibrated against the red line plus the gray line, which is the confidence intervals around the numbers. But where you see that we were not able to calibrate it right is in the cases of the numbers of infected. And you can see that the official numbers arising from the testing are way too low against what must have happened to produce the people in the ICUs and the people being hospitalized. Because there we are trusting the transition probability from being infected to being hospitalized to being in the intensive care more than the absolute numbers of the infected. And this difference between the observed and the simulated numbers of infected is also observed by Kai Nagel in his simulations for Berlin and others as well. And it is interesting to see that few countries are able or willing to do random sampling of the population to establish their status as far as having been infected or being currently infected. The British or the English are doing a reasonable job there, but it hasn't helped them with the other management of the disease. But this is something which all the countries should have done. Anyway, so we're able to calibrate the model at the national totals pretty well. And that is true for all of these epidemic models. You can calibrate them well against national totals. Or if you're interested in a limited area, which is clearly defined and locked away, you can do that. But we were not able to do so at a subnational level. What you can see here are the results for a couple of the Swiss cantone, which are the lower levels of government, actually, depending on how you look at it, are the government of the country. And you can see that, for example, if you take the example of Basel-Stadt, which is a city canton, essentially it's a city and one or two suburban villages, we are matching the numbers pretty well. It's not too bad. But if you look, for example, at Schwyz, which is a tiny rural canton, you can see that we're way off. The problem we have is that, yes, we are modeling the travel between the cities as well, but we might not model it as well as we think. Plus, we don't really know where the infected people arrived in the first place. So here, we could either obviously force and get it right, but this kind of adding fudge factors didn't appeal to us. So we kept it at that. So yes, the national numbers we are producing well, the local and regional ones only in exceptional cases. And this is further work for a later stage for us to do. This is kind of as results is the average cases in ICUs in the different hospitals in the country. What is relevant here is that there's a couple of big hospitals, in particular the university hospitals, and many smaller ones around the country. And that obviously doesn't make it any easier because we don't really know who is in which hospital. So we can't really trace those cases to their spatial origin. So we have a further issue here. Sorry. What we can do with the model is to look at the vaccination strategies. And you can see at the right side of the graph, the impact of vaccinating different numbers of people in the country. And you can see that we need massive amounts of persons vaccinated every day to achieve the impact we want to achieve. As we all know, that our original hope or expectations, which many people had, that the vaccination would stop us from being at risk of the disease has not materialized. We now do know that there are people who get ill a second time or first time and are able to spread the disease even if vaccinated. Yes, there are much lower risk of becoming seriously ill, so it's a big gain, but it's not a panacea. And it doesn't help that in Switzerland, like many other countries, not everybody is willing to get vaccinated. Switzerland is now at a stage where we have about 60% of people vaccinated. We have about 20% of the population who are vaccinated by having been ill. But we have still about 20% of people who are, if you're a cynic, are waiting to be vaccinated through the disease. And we can only hope that they change their attitudes and get vaccinated before that happens. Sorry. We are now trying to expand the model because we do know that prior conditions affects the seriousness of the disease. So we will include in the model, in the descriptions of the agents, various health status variables. For example, if they are diabetic, have hypertension. And we can take this from a national survey of the health status, which allows us to impute these conditions to our agents. And then we will be able to look more closely at what impact that has on the regional numbers, because these numbers are probably regionally clustered, as well as on the chances of people getting ill and hopefully then spreading the disease as well. Now, what are the next steps? We have this project, which is funded by the Swiss National Foundation, to improve the capabilities of EpiSim and MatSim to help with prediction of future pandemics. We want to look at household interactions, which are currently not included because MatSim isolates the agents. But we do have information about their household structures. So we want to look at household interactions and therefore the joint travel of people, which obviously is a capability which we would like to have anyway. We have access to the UK National Travel Diary Survey, which gives us weekly household data. Then we want to work at implementing large events, which is something which traditional transport models and agent-based models have never really worried about. But clearly in the pandemic, we have learned that a church service or a political rally or a football game or whatever large event, a wedding, can be a super spreader event. So we want to include super spreader events by looking at where they can happen in terms of room sizes, as well as the number of people attending them. Then on the methodological side, we want to improve the pipelines to make the activities more detailed so that we look at their different activity types, whether indoor, outdoor, whether it's sports or whether it's something seated, and the location assignment. We will look at Bayesian networks for generating the household interactions and weekly activity patterns. We will, as I said, model superspread events, and we will continuously update the illness propagation in the population so that we get a better handle of how the epidemics might work. Now, we are at question time in a second. I just wanted to let you know that there's a website where we report our work, in particular on the ongoing tracking study, plus all the other papers we are writing. And because the colleagues in Berlin are doing so much with EpiSim, I also list the websites in Berlin, where Kai is publishing about every 2 weeks the latest of his results. And then finally, the website for MatSim, where you can download the code, and you have zillions of books and reports to help you get started. Any questions, I'm happy to take.
Thank you, Kai, for a great presentation. We have some questions in the chat. So Ricardo asked, thank you a lot for your interesting presentation. How do you calibrate estimate values like the probability of someone being infected in relation to how ventilated the place where the interaction took place was? Do you have any data to validate your results at this more disaggregate level?
No, we didn't try to do that. There are some studies which help you to look at the relative risk getting infected indoor, outdoor. But inside the EpiSim approach, we just calibrated against the total numbers. We didn't really go down at that level.
We have another question for Marisol Castro that was, what are the data requirements to implement a model link like MatSim from scratch, like the minimum requirements?
The minimum requirements are more or less what you need for any transport model. You need a network, you need the timetables, and you need a description of the population and a travel diary. So the usual things, but nothing really much more than that. Because in the end, we are just looking at the issue in a different perspective, but we are still using the same inputs. So there's nothing more. At this stage, with all the pipelines we are providing, our estimate is that we need about 4 to 6 weeks to get started. And this is kind of demonstrated by some of the recent models we built. We built a model for Sao Paulo, we built a model for LA, essentially with published data from these cities and for Paris. And actually building it is one thing, and then the calibration is the next thing. 6 weeks to 8 weeks when you have the data.
Thank you. If anybody has any questions, you can raise your hand. In the meantime, I can ask you some of the questions I have. So I wanted to know the vaccination. You did mention that your vaccination rates weren't as great in Switzerland as in other countries, or as you expected to be. Is this included in the infection rate and also in the progression rate? So people don't get, like, the mean and standard deviation of getting seriously ill is lower than when you're not vaccinated, or no?
Okay, that's a good point. And at this point, EpiSim is being expanded to cover those subtleties of the process. The results I showed you were before those extensions were implemented, but you can implement those effects as well.
Okay.
Juan?
Yeah, Juan.
Hi, Guy. Many thanks
Hi,
for the presentation. I just wonder whether these results have been used by policymakers or public policy, to which extent, how you envision this may be used in practice, how the communication goes on that side.
Thanks. In our case, our results are mostly based on the tracking study, because we are giving the tracking study results every week or every 2 weeks to colleagues here at ATH, which they are using in their predictions models for the federal counselors for their decision making. So we are not directly involved in decision making, indirectly. Kay Axhausen is a different proposition. He has been directly involved in the scientific discussions, which are then handed over to the ministers to decide. And that's, I think, is the proper way of doing that, is to essentially provide the numbers and let a committee decide. And what is important, that a committee or a group of people aggregate all the different results, because ours is just one approach and there are other approaches. And I think if you want to do policy well, you should look at all the different approaches, look at their results, look at their insights, and then take a decision.
Many thanks.
We have a few questions in the chat window. So the first one is from Benjamin Gramsch. Hi, thanks for the presentation. Do you consider the impact of middle school on the spread of COVID, as kids tend to be asymptomatic and have close contact at school?
Okay, here we have an omission, and that's a good one that I should have pointed out. The populations we are using in MATSIM are generally only starting at 16 and above, which has to do with the fact that that the StatPop, which is the source of our data, doesn't include children, or doesn't give us access to the children. But we could include them if we had access to those numbers, either directly from the population registry or by imputing them and generating the proper population. Yes, we should have done that, but we don't.
Sorry, another question from Sebastian Seriani. Hi, Kay, very interesting presentation. Maybe you mentioned it, but I would like to ask you more details. Did you study the relationship between car speed, mobility, and people infected? Did COVID increase the speed of cars on streets?
Obviously, we didn't use the simulation, but we looked at the impacts of speeds, the impact of COVID and travel on speeds. There is a standard analysis of the data, which we publish every 2 weeks. And in this report, we do show the different levels of speeds in the country. And we are refining this to show the results for every one of the major cities. And yes, we are seeing quite massive impacts on the speeds. For example, I have the numbers for Zurich at hand, and there the difference between the before period and during lockdown, when travel was down by a factor of 50–60%, we saw on the urban roads an increase of about 5 to 6 kilometers an hour there. And on motorways, the increase was even higher. So yes, we can get an idea of the capacity impacts of MOBIS, of COVID, or any other major reduction of demand this way. And we are planning, or I'm planning, to publish those results separately in the near future.
Thank you. So we have another question from Ricardo Ortubia. Has there been any further progress in the integration of land use models in MATSIM since the Sustain City project? Do you see any way to use long-term modeling, including urban form, to explore which type of city is better to deal with issues such as this pandemic?
Now, this is obviously two big challenges. The one is, can we say something about city form and the impact of the pandemic? And the second thing, can we integrate this into a transport model? Yes, Sustain City was a first attempt. Rolf Mökel in Munich worked together with Kay Axhausen to integrate his land use model with Matsim and made good progress there. But as we all know, land use transfer modeling is very involved and very difficult. So I leave that to other people. Now, on this impact of city form and the pandemic, I would, in the first instance, assume that there is very little impact of city form on the pandemic, because what we are talking about is the network of co-presence. And the network of co-presence is driven by social needs. And I would assume that the social needs are the same in every city form. Now, before you shout at me, yes, I do know that in different cities, you have different densities, and particular groups of people have to live at higher closeness to one another. But then if you look at the difference of the impacts of COVID in a place like Hong Kong and the cheaper parts and the poorer parts of LA or Atlanta, you see a big difference, which has to do with the way in which the people handle the disease. So yes, in the US, having been poor, exposed to much higher risk than being rich. But there we have to then also account for the fact that you have this essentially dysfunctional American healthcare system in which poor people are just too afraid to admit that they're sick, and even if they know they are sick, to go to the doctor. So there's a couple of extra elements which you would have to include there. So having said that, yes, it would be great if we continue to work on the integration of land use transport modeling, but I'm not sure whether this is all it needs to get at a better outcome for the poorer population.
Great, thank you. If we have last questions, somebody wants to raise their hand? Yep, well, so we're just on time, so that was perfect. Thank you, Kai, so much for attending this conference. We really appreciate it.
My pleasure.
Thank you so much for your great presentation. And I hope sorry, Juan Antonio is clapping, sorry. So
thank you.
Okay, so thank you so much. Thank you everyone for attending. And I hope you're enjoying the conference, and we hope to see you in other sessions.
Thank you very much. Bye-bye.
Thank you, Kai. Bye.
Have a good day.
Thank you.
Bye.